when you have a look at this diagram, it's a bit tricky because you start to get lost in, you see why now I didn't put on any more labels because it's already pretty confusing, okay? The first thing you got to do is you've got to try and get theta in the picture. You've got to get theta in the picture so that you can do your sines and coses and trigonometry just like we did over here, okay? I think you can probably see, for instance, if I go from theta to here, right, see this angle? This is a 90-degree angle because it's the intersection between the horizontal and vertical forces, right? So being that that's a 90-degree angle, this is 90 minus theta, but this is 90 over here, that's also a right angle. So you've got 90 minus theta, that leaves theta up here. Does that make sense? So you should have it up there. In the same way that I did alternate angles in this diagram, you've got theta over there as well, okay? So if you went ahead and drew your triangles carefully, what you would have found is you've got this component going along the normal, and then you've got, where am I going to write it? Up here. This component going along the tangent, okay? So now we have all of the pieces. We have accounted for the horizontal, we've accounted for the vertical, and now we can add everything up, okay? So we're under uniform motion, okay? Let's think about the normal first, the normal, because they're both kind of headed in the same direction. Does that make sense? Now, when you're doing the normal, all you have to do is add up, okay? Well, I've got Fy sine theta, and it's positive because it's going away from the origin. And then you've got Fx cos theta, right? So that's all good. But I know what Fy and Fx are. I spent all that time developing that table, going all the way from displacement, differentiate all the way down, multiply by mass. What do you get? What is Fy times sine theta? And if my memory is serving me, I think you should get minus mr omega squared, I think. I think this one was cos theta, so you're going to get sine theta cos theta. Yes? Isn't that what I did? What have I got? Oh, right, sorry, it's squared. I'm thinking of the other one. I'm doing the wrong one. Better? Cool. You play the same kind of thing with your horizontal force multiplied by cos theta, so you're getting this. Cos squared, okay? And you're like, hold on. Sine squared plus cos squared, just the Pythagorean identity there. So these both add up to 1, right? So then, what are you getting? You're just getting minus mr omega squared. Now, just pause for a second. Do you remember when we played our game and considered the vector in one spot and then the vector in another spot? We added them up together and then we compared the change. And we found the acceleration was pointing toward the origin, right? And that was kind of like a nice fancy geometric trick. But have a look at this. Can you see why this tells you exactly the same thing, right? This negative sign means being that this away from the center is the positive direction, then the negative means you're going back in that direction, okay? So along this axis, that's the force on the normal, okay? It's pushing you back toward the center. The word we had for that was centripetal, remember that? Okay, let's have a look at the tangent now, right? So, be careful with this one though, because your horizontal force, right? You see how it contributes this force, but it's going in the wrong direction, right? It's going down this way, okay? So therefore what you're gonna have is make sure I write this right, Fy cos theta, that's going in the positive direction, but then you're going to subtract Fx sine theta. Is that right? Does that make sense? Okay, now this is what I was thinking of before. Because Fy has the sine in it, when you multiply by cos, that's going to give you minus mr omega squared sine cos, right? Then you subtract, because it's going in the other direction. But then when you just substitute this in, you've got another minus, right? And it'll be mr omega squared. It'll also be sine theta cos theta, right? Okay, so what does this mean? It means these two exactly cancel each other out. These two are going in opposite directions in the same magnitude, right? So your force along that tangential axis is 0. Why is that? Because the whole scenario we started with was that omega is a constant, right? So I'm going around at a constant rate. I'm not speeding up as I go around. I'm not slowing down. I'm just going around at a uniform rate. So there's no force along this tangent axis that's speeding me up or slowing me down, right? If this was positive, I'd be going faster and faster and faster. If it was negative, I'd be getting slower and slower and slower, okay? So, a couple of things. Before we leave off uniform motion, you might notice you've got your omega there, right? That means that, how long does it take me to go all the way around? In other words, what's the period of motion? Because that's how long it would take me to get back to the beginning. You can get this straight from omega, right? How far do you have to go to make one full revolution? Answer, 2 pi radians, right? Period, right? This is time. This is distance over speed, right? But speed is omega. That's how fast I'm going around, right? So that's the period, okay? In exactly the same way, you can say, well, what's the frequency? How would you work out frequency from that? Think about it. How do we usually go? You know when you think of trig functions, right? These guys. Which, by the way, are exactly the same as what you have here, okay? How do you go from period to frequency? Period to frequency? 1 over, it's just, isn't it just the reciprocal of this? It's just the reciprocal of this. It'll be omega over 2 pi. Now, it's not that you have to remember those. For me personally, my brain goes immediately here rather than here. But the questions will equally give you either. It'll say, it goes around at a frequency of 500 whatevers per minute or something like that. Or they'll tell you, it takes me 15 seconds to go all the way around. So you'll see both of them. Okay. So that's the last thing I'm going to say about uniform circular motion before I give you an example. I want to mention non-uniform circular motion before we leave off, because there's a bunch of questions which are just like this, but rather than omega being some kind of constant, right, what they say is, well, omega can change, right? Omega can speed up or slow down, right? Now, think about it like this. How do we get to these forces? How do we get to here, right? Well, I can do a bit of a shortcut for you. Do you remember when we did our diagram? We said that velocity, we just went from the arc length formula, right? The velocity along the tangent is equal to, now I think if I remember this right, I've got it written down here. It's just going to be r times omega, right? Does that make sense? And that's how we got that the further you were away from the center, you know, like that poor person on the outside of the circle, okay, the faster you had to run, right? Because this gets bigger. All right, so how would you go to acceleration along the tangent if omega was not a constant, if it were a function? Now, I'm not telling you what the function is. It could be anything, right? But the point is, well, r is going to be a constant, so I'm just going to chuck that out the front, okay? And then you're differentiating with respect to time. You're doing this. Make sense? To get to a force, you know, this kind of thing, right? The force along the tangent is just going to be this multiplied by mass. Okay? Now, in order to maintain its circularness, okay, so that I don't spirally and like, you know, sort of crash into the origin, or do the reverse, not have enough force holding me, and so that I just, you know, I go off and I don't stay within orbit, I suppose, okay? What you can say is that this is the force along the tangent. Well, the force along the normal has to be exactly the same as this. It has to be the same. If it's not exactly precisely equal to that, you won't get a circle. Okay, and this circular motion, right? That force that you get, it can result from a whole variety of things that's pulling you back toward the center. For instance, it could be. Now, pause for a second. Think about this. Think about this. Okay, what's the force keeping the keys in circular motion? Because there's a force keeping them there. Otherwise, they wouldn't do this, right? I'm trying the best as I can to make it uniform, okay? So we've got this zero force, okay? What's holding it in? Now, we don't usually think of it in these terms, right? But this lanyard, right? This lanyard is exerting a force, okay? Now just consider this. At the moment, I can't, oh, here we go. I'll do it like this, right? At the moment, this lanyard is not exerting any force, right? Because it's nothing's holding it tight, okay? But the second I do this, the lanyard goes out straight, right? Now we have a name for that. We call that tension, okay? There's tension in the, what's it called? In the lanyard, right? If there was no tension, if it was like, say, what's a substance which has no tension? Like something like Play-Doh or something. It would just stretch out and it would go forever. The force that's pulling this out, right? Because you know how there's this force, right? What was the third law of motion? There's going to be an equal and opposite force going in the other direction, right? So some people call that centrifugal force, right? So that reaction force is trying to pull away, okay? So if there's no tension in the lanyard, it'll just fly off. Whee! Okay, so I should watch this more carefully. But there is tension in the string, okay, in the lanyard. And that's this tension here. It's holding it in circular motion. Now, by the way, there's plenty of other things we know in our common experience, even if we don't. I mean, we see them up in the sky. What other kinds of things are going to hold things in circular motion? Things like, say, gravity, right? So that's holding things. Like, I don't, if I put an earth here, whee, there's an earth, okay? This thing is exerting that force along the normal, and that's gravity. We're familiar with that, right? So this force, or that force, it's the same thing, okay? You can get it from gravity, you can get it from tension, and you can get it from a few other places as well that we're going to notice in the following week, okay? But that's the important thing. That's what this represents.